All right, so in this video, we're going to look at the first part of chapter 19. Now, something I'll go ahead and point out is that I'm going to go into a little bit more detail with microstates than the book does with Boltzmann and that kind of thing. I think it is really good for you to understand the statistical analysis of how molecules move and how that relates to the big picture. So there's going to be a couple things in this video that will not show up in quite as much detail in your textbook, but let's jump into chapter 19. So the first thing is we do chapter 19 and chapter 5 together. We do thermochemistry in chapter 5, and now we're going to look at thermodynamics in chapter 19. Something that it's really important that you keep in mind is that you cannot create or destroy energy, okay? That's kind of self-evident in chapter 5 and in the first law that we looked at there. Logically speaking, we can conclude that if you can't create or destroy energy, the total energy of the universe is a constant. It is unchanging. However, okay, the energy can be converted from one form to another. You can transfer it from a certain system to the surroundings or from the surroundings into a system. Okay, so we can move energy, but energy is never created or destroyed. So we have to kind of balance it. Okay, now we have looked at enthalpy a little bit, and we know that enthalpy is the heat absorbed by a system. We studied it under constant pressure. In this, chapter 19, in this video, we're going to look at entropy. And entropy is something we looked at in year 1 chemistry, right? When we talked about randomness or chaos of a system. But both enthalpy and entropy are related in the fact that they're going to determine whether or not a process is a spontaneous process or a non-spontaneous process. Well, what do I mean when I say spontaneous process? Well, a spontaneous process happens spontaneously, right? It happens without any outside help. So if we look at the gas that we have here in this this closed container, all right, then it's closed by this stopcock right there. When we open the stopcock, then we can expect that gas is going to spontaneously effuse, right, move through a small hole from flask A over into flask B. That is a spontaneous process. However, it's not going to go back from B to A. So that process that we see down here is not spontaneous. All right, what's wrong with my pad here? It's working. Sorry, hold on just a sec. There we go. Okay. So a process that is spontaneous in one direction, by definition, is going to be non-spontaneous in the reverse direction. Another great example of that is dropping eggs, right? If you drop the eggs, they will spontaneously fall, they will spontaneously hit the counter, and they will most likely spontaneously break. However, you can't pick those eggs back up and, revert them to a nice state of being inside the shell, right? So that's non-spontaneous in the reverse direction. Now, there are factors in our experiments that we can use to affect whether or not something is spontaneous. Both temperature and pressure affect spontaneity. Think of ice, right? So if I just have water sitting out in my driveway on a summer's day, it's nice 60 degrees, that water is not going to spontaneously freeze. However, if I take that water from my driveway and I put it in my freezer where the temperature is, at or below 0 Celsius, then the ice is going to spontaneously freeze. So you can change spontaneity based on changing temperature, or, obviously you could also change pressure, right? Think about boiling water, right? If you can adjust the pressure in a vessel, you can get water to boil at a much lower temperature than it normally might. So lots of different ways we can affect spontaneity. Now, when you're thinking about reversible and irreversible processes, we want to kind of think of them in terms of descriptions, like these two models we have here. We have the system and its complete surroundings, and then on the right we have partitions and pistons and that kind of thing. So in a reversible process, the system is going to change in such a way that the system and the surroundings can be reverted, right? So they can be returned to their original state. Now, if you do a process that is reversible, this is going to maximize the work that's being done on the system. All right, we're going to maximize that work, okay, by the system on the surroundings. Now, just for clarity's sake, most processes are not reversible. Okay, so this is again one of those in theory kind of things. There are not very many reversible processes. And we'll get to why shortly when we talk about entropy. An irreversible process cannot be undone by reversing the change to the system. All right. Spontaneous processes are always irreversible. That's something that's really important to know right here. Okay. So like if we have this vacuum here, right? So there's our vacuum, and we move the partition up out of the way. We know that the gas is going to expand to occupy that available volume. However, if I want to get it back, okay, I would have to do work with this piston to compress the gas before I could drop that partition back down. And so since I can't get it back to this initial state without doing work, we say that it is an irreversible process. Now, entropy measures the randomness in a system. Entropy is a state function, and like all state functions, that means the change in the state function is equal to the final position minus the initial position or initial value. So since entropy is a state function, we use S, capital S for entropy. So we would say delta S is equal to the final entropy minus the initial entropy. It can always be found from heat transfer. So remember that Q is heat transfer, okay? And as long as we know a given temperature for the heat flow that it's occurring at. So we would say that delta S is equal to the heat transfer or the reversal of Q, the movement of Q in reverse, the heat transfer divided by the constant temperature. The units for entropy are joules per Kelvin. As you can see here, right, we know that Q would be in joules and temperature has to be in Kelvin. So delta S is in joules per Kelvin. Now, this brings us to the second law of thermodynamics, right? We're going to take what we just talked about with entropy, and we're going to add it to reversible and irreversible processes. So the entropy of the universe increases for any spontaneous process. That's the second law of thermodynamics. If you have a spontaneous process occur, the overall entropy of the universe must increase. This gives us two relationships. If you have a reversible process, then delta S of the universe can be set equal to 0 because the delta S of the system and the delta S of the surroundings are going to be interchangeable, and so you're going to get 0 as your total thing, as your total entropy. For an irreversible process, and this is the one that we're going to see most often, the delta S of the universe must be greater than 0 once we have kind of balanced all the books, as it were. So let's look at this from a molecular scale. We talk a lot about in chemistry about, relating the molecular behavior of individual components to the big picture that we see. But let's kind of see an example of that, right? And in order to do that, I have to talk about Mr. Boltzmann. So Boltzmann is responsible for describing entropy at the molecular level. So if we look at this this little gas movement apparatus that we have here, we have two molecules of gas, a red molecule and a blue molecule on the left side in picture A there. If we open up our little stopcock and we want to know, okay, after the gas moves around, what is the likelihood that they both end up back on the left? We can see the four possible positions of those molecules here in picture B. And we call those possible arrangements a microstate. So we could have blue on the left and red on the right. We could have red on the left and blue on the right. We could have both on the right, or we could have both on the left. So they've drawn them out. So in this case, all right, the total probability that both of the molecules end up on the left is actually 25%. It's a half squared. Well, what if we scale that up to a number of molecules that we can maybe see, like a mole of molecules? Well, then it would be 1/2 to the 6.02 times 10 to the 23rd. If you punch that in a calculator, you actually get 0. That's pretty much no chance, okay? And the reason for that is that gases are going to fill the volume that they're given. We know that's true, right? That's a spontaneous thing. Gases are going to spontaneously expand in order to fill whatever volume that we give them. In this case, the most likely position or the most likely arrangement that we're going to see is going to be approximately an equal amount of molecules on both sides. Now, if the world were comprised of, little teeny tiny in this case, two atom or two molecule systems, well, number one, we wouldn't be here. And number two, that would be really boring. The fact of the matter is, we are big picture molecules, trillions and trillions and trillions of molecules that are all interacting. So in thermodynamics, we try to look at the bulk property of a substance in order to examine the big picture of what's going on. We just now looked at what's on the molecular scale. How can we relate that up? Well, basically, we have to look at it as a probability system. And if you study statistical thermodynamics, that is what you're studying, the probability or the bulk properties of a substance. In order to kind of go further with this, I need you to know the word microstate. So a microstate is a snapshot of all the positions and velocities of particles at a single moment in time. So we're going to look at that. Now, Boltzmann uses microstates because or talks about microstates and points out that you can't actually look at all of the different microstates in a given system. So think back to 2 slides ago, right? We had 2 atoms in our little gas movement apparatus. We could draw out each microstate, right? There were 4. But when you start talking about a mole of gases, imagine if in each picture you had to draw 6.022 times 10 to the 23rd little dots, and then you had to track where each one went, because there's multiple places in 3-dimensional space where each molecule or each atom of the gas could be, and you'd have to draw that for each one. That's like impossible. We use W in order to represent the number of microstates that are possible in a system. And we can calculate entropy based on how many microstates are associated with a macroscopic state. So we're relating microstate to macroscopic state. The formula that we use to do this is right here. Entropy equals K ln of W. K, all right, is Boltzmann's constant. It's 1.38 times 10 to the negative 23rd joules per Kelvin. W is the number of microstates, and S is going to be entropy. Ln is natural law, button on your calculator. So the idea behind multiplicity is simple. How many different arrangements or different microstates are possible in this box, all right, if you only have one shape per box, one X per box? So in order to calculate multiplicity or look at the number of microstates available, we use a factorial. And you've probably seen factorials in your algebra class. The formula that we use to find W, the microstates, is right here. We do M factorial, where M is the number of available positions. So in this case, how many boxes do we have? We have 3 on the left, 3 on the right, so M is going to be 6. And X is the number of particles, and I just happen to use X's in my pictures. It could be, whatever. So we do M factorial over X factorial times M minus X. So the total number of positions minus the total number of particles, factorial. So in this case, we have 20 possible microstates. So if we call this like X1, X2, and X3, there are 20 different pictures you would have to draw in order to put all of the X's in their respective places. Now, if we want to calculate the entropy of the system, now that we know that there are 20 microstates, we do S equals K ln of W. So plug it in, and we find that in this specific 2-dimensional system, the entropy is 4.13 times 10 to the negative 23rd joules per Kelvin. Now that's great and fine, right? But if you don't have anything to test it against or look at it against, it doesn't really do us a lot of good. So let's compare it to another system. Let's look at this system. So here we still have 6 potential places to put our little circles. In this case, x is 2, they're 2 particles. So 6 factorial over 2 factorial times 4 factorial, right? Because we do 6 minus 2 to get that number, right? We do 6 minus 2, okay? And that's going to tell us there are 15 microstates for this one. So again, what's the entropy? Let's find the entropy. In this case, we get 3.737 times 10 to the negative 23rd joules per Kelvin. All right, let's compare them. System A, System B. There's more entropy in System A, right? The number is greater, 4.13 compared to 3.737. There's more entropy in System A than in System B. Well, why? Well, there's more multiplicity. There's more microstates, right? Remember, we had W was equal to 20 in System A, or W is only equal to 15 in System B. So with greater number of microstates, you have greater randomness, right? So that's higher multiplicity. More randomness equals more entropy. So System A has 20 microstates, System B has 15 microstates. What would happen if we combined the system? What does the second law of thermodynamics tell us is going to happen if we combine these two systems? Well, so we take them, we put them together. Now we have 12 potential positions. There's 3 x's and there's 2 o's. So this is my factorial setup. So I do the number of x's, the number of o's times the number of x's times, and I'm doing m minus x minus o here. That's how I'm getting this bottom. All right. And so you can punch that into your calculator. Now, in case you don't know how to do that on a factorial on a calculator, let's see, this is the 84 plus. So give me just a second. I think it's under math. Yeah. So if you go to math, so underneath alpha is the math button, and then you go to the right 4 times to PRB, which is probability. Number 4 is the exclamation point. So you can get to it there. I also think there is a shortcut. I know there is on my other calculator. Alpha, maybe. Oh, there's a question mark. No, I don't see one. So probability, and you go over to number 4, and there's your factorial. Anyway, you plug that in, see what you get. I'll give you a second. You should get 7,920 microstates. So we went from 20 and 15 microstates to now almost 8,000 microstates for how we're going to draw that out. What would the entropy be now? Well, same thing. Boltzmann's constant times the natural log of our microstates gives us 1.239 times 10 to the negative 22. So this is a whole order of magnitude greater in entropy. And so we have a massive increase in entropy, and that jives with our second law. If you want to work one on your own, try this one out. I'll give you a hint. You're going to get a really big number of microstates. So since entropy is a state function, all right, looking at entropy in the microstates, the final value of entropy in a system minus the initial value is going to tell you the overall change. So if we want to look at how that relates to that Boltzmann equation that we just looked at, well, now we're just going to change from what we had before, right? We had S equals K ln of W. Well, now we're going to add the delta. And so we need to just have final and initial microstates. So using our logarithm rules, we can rearrange this, right? When you subtract a logarithm, that's the same as dividing the answers. And so we can say that delta S equals K ln of W final divided by W initial. That's a really useful kind of rearrangement ability to have, by the way. If you're not familiar with rearranging with your log rules, that might be something you want to look at from your algebra notes, all right? Anyway, so if I want to find the overall change in entropy from just microstates, I can do that right there. So K ln of the final number of microstates divided by the initial number of microstates. Basically, if you increase the number of total microstates, you should have a positive entropy change. More entropy equals more disorder. That's what we're after. Now, there are some other things that can affect the system, right? We can look at volume and temperature. If you increase the volume, what would that do to microstates? Well, increasing the volume means there's more positions available for our molecules to fill, and so we should have more microstates, and so we should have more entropy. So an increase in volume should increase entropy. If you increase temperature, then your average kinetic energy of each molecule is going to increase. So you're going to have a greater distribution of molecular speeds, and so there are more possible kinetic energy values, so there are more microstates, so you should have more entropy. Now, when we're talking about these molecular motions, there are a couple molecular motions you need to be familiar with in order to kind of describe this change. There's translational molecular motion, where molecule moves from point A to point B. So it's translated across, say, some distance. There is vibrational molecular motion, in which case the atoms within a molecule are moving, and so maybe the bonds are moving a little bit, or there's some twist, something like that. There is rotational molecular movement, where, let's say, the water molecule here at the bottom, it's not moving from point A to point B, but it is turning in three-dimensional space. And so the more atoms that you have in a system, the more microstates there are, because you have the potential for more combinations of molecular motion. So there's a lot of different molecular motions, okay? Make sure you know those three. And just keep in mind that the more molecules you put into a system, the more potential arrangements that they have based on their vibration or their rotation or their translation through space. So when we kind of take those things and we put them together, then the number of microstates and therefore the entropy is going to tend to increase if you increase temperature, volume, or the number of molecules in a system. And that should make sense, right? When I made system A and B and put them together and I made them bigger, well, then we got an increase in entropy. When we compared system B, which only had 2 molecules in it, 2 particles, to system A, which had 3, system 3 with more molecules, right, more particles, had greater entropy. Okay, so we've seen that. We also see it with the physical states, all right? What we use to describe that is called freedom of motion. And we can say that the entropy is going to increase with increasing freedom of motion for a molecule. So the entropy for a gas is greater than the entropy for a liquid, which will be greater than the entropy for a solid. If you are forming a gas from solids or liquids, you're increasing the entropy. If you are forming a liquid or a solution from solids, then you're increasing the entropy. And if you have the number of gas molecules increasing overall during a chemical reaction, so in order to identify that, you would be looking at the balanced coefficients, then you're going to increase entropy. Now, I cannot state this high enough. These 3 things right here are exceedingly common test questions, AP test questions, short answer test questions. So make sure you look at those. I've tried to assign some problems this week that will go with that idea, but you're going to see that also when we start practicing our multiple choice questions for the AP test, and when we're looking at the short answer questions you've been kind of working on. So we'll see some of those, all right? Now, in the second video, I'm going to look at the third law of thermodynamics, and we're going to get into Gibbs free energy and spontaneity. All right, so this is kind of the end of part 1. So if you have any questions about part 1, just make sure that when you email me, you say, hey, in the part 1 video, XYZ. All right, so I'll see you guys in the next one.